20 minutes coffee break.
Yes, we used it for questioning, and we ran over the time.
Well, can you get 5 minutes break?
5 minutes. So maybe we need time to check for presentation of by the two speakers. So
Sure.
so can you Professor Jack and Dr. Nishiyama hear me?
Hi.
Yes.
Hello.
Oh, okay. Long time no see here.
Yes.
Jack, how is it going?
Pretty good.
Okay.
Pretty good.
Okay. I'm pleased to hear that.
Let me.
Yeah.
Okay. Let me try to see if I can share my screen.
Yes, go ahead.
Okay. I see. Can you see it?
Yes.
Can you see the presentation?
Yes, it's okay. Yes.
All right.
Now, full screen of your presentation.
Maybe I'll just keep it on in case something goes wrong. I prefer to have it on, if you don't mind.
Okay. So, can Dr. Nishiyama hear me?
Yes.
So,
Yes. Okay.
please try to upload your presentation.
Okay, I start. Oh. Professor Tuszyński is using the
maybe I should stop sharing.
Okay.
Okay.
Can you see
yes, I
our
can
slide?
see your presentation, Dr. Nishiyama.
Okay.
Yes, it's okay.
Okay. Okay.
Okay, so Professor Chenkova.
Yes.
What time we start? So
we are starting when you're ready.
Okay. Okay. So okay, I ready. So okay. So okay. So this is Jack's presentation. Okay. So hi, good morning, everyone. I'm a chair in this.
Morning.
Okay. So can I speak?
Absolutely.
Yes, please.
Okay. Okay. Hi. Good. Just a moment. Hi. Good morning, everyone. I'm a chair in this section, Hiroshi Murakami from QST, instead of Professor Tanaka, Kobe University. Unfortunately, he's absent today. Also, I thank him, the Professor Tanaka, for my first time to attend this excellent conference. I've got to know the two speakers here owing to Professor Tanaka. So afterward, we have nice time for discussion about their brain model. The two speakers here are theoretical physicists, but the first speaker, Professor Tuszyński, is also into practical things such as microtubule. So as for Jack's biography, so he obtained his Ph.D. in condensed matter physics in 1983 from the University of Calgary. From then to 1988, he was a faculty member at the Department of Physics of the Memorial University of Newfoundland. Newfoundland. Now he's full professor at the Department of Physics in the University of Alberta. Between 2005 and 2020, he has a prestigious Allard Chair in Experimental Oncology at the Cross Cancer Institute. He was also fellow of National Institute for Nanotechnology of Canada and held visiting professorship and research position in many countries such as China, Germany, France, Israel, Denmark, and so on. And the major thrust of his computational biophysics group is in silico drug design for cancer chemotherapy applications. So, Jack, are you ready to start it?
Yes, I am. Thank you very much, Hiroshi, for this nice introduction. And thank you, Rumiana and Yelena, for inviting me to this wonderful conference. Without further ado, I just want to tell you that I will actually present mostly experimental work today because there's a lot of interesting results I would like to share with you dealing with electrical properties of microtubules, involving their conduction, capacitance, electrophoretic mobility, and also interactions with electromagnetic radiation, including very intriguing delayed luminescence effects that were discovered by my collaborators, specifically Dr. Dogari from the University of Central Florida. Let's start from the beginning. What is a microtubule? Microtubule is a protein polymer, cylindrical in shape, built from tubulin dimers alpha, beta, as shown here. It's a very important structure in the cytoskeleton of all eukaryotic cells. It is involved in various important roles such as cell migration, macromolecular transport in cells, as well as chromosomal segregation. Microtubules make mitotic spindles, and this is why I was interested because of the involvement in cell division and therefore an important role in being a target for chemotherapy. But here we'll be talking only about electrical and electromagnetic effects on microtubules and tubulin. Microtubules are very dynamic. They grow and shrink at rapid rates and undergo something called dynamic instability. What is even more perplexing and less known is that they are incredibly exotic, if I can use this word, electrical devices. They show variable resistance, capacitance, act as transmission lines for ionic conduction, also memriscence, so they have actually memory effects displayed in their properties vis-a-vis ionic flows. And this is the structure. It's a cylindrical structure with 25 nanometer outer diameter, a lumen, basically a void, 15 nanometer in diameter. And as you can see here, there are two types of lattices typically formed, regular lattices on the surface of the cylinder. Microtubules have extraordinary electrical properties. Tubulin, which is the building block of microtubules, is a heterodimer shown here. It's important to recognize C-termini. I'll be coming back to their role. C-termini are about 15 to 18 amino acid protrusions, and they carry about 40% of the electric charge of tubulin. I'm sorry. The dimer charge of the dimer is about 50 negative unit charges. As you can see here, that's a distribution of all known proteins with their charges, slightly negative on average, but tubulin is completely an outlier. And the dipole moments, likewise, the dipole moment of tubulin heterodimer is something around 2,500 dBi. Compared to water, it's about 1,000 times greater than water. And if you build a microtubule, then you'll be creating some very dynamical electrical effects. I don't know if this will show. Yes. So gliding assays show microtubules drift and move towards positive electrodes. They're negatively charged, so they will be moving towards cathodes. And you can align them in strong electric fields. That has been published in the past, but we wanted to quantify these effects and understand how these effects also scale up, because microtubules not only exist in free form, but they create more complex structures such as centrioles, as well as cilia and flagella, used in single cellular organisms in their propulsion and motility. So this is a very sort of summary-like outline of the mechanisms of interaction of microtubules with electromagnetic waves, and different frequencies are involved in different mechanisms, from acoustic waves in the 500 kilohertz to all the way to the visible range, as you will see at the end of my talk. In the middle, you also see very interesting excitations of ionic waves around microtubules from 0.1 to 1 megahertz. And I was very interested in the range about 100 kilohertz, which is actually currently used therapeutically to treat brain cancer. And we wanted to know if microtubules play a role in this. So that there are variable effects. As a physicist, I'm interested in what really is happening, what is the mechanism. And ions are attracted to microtubules, they get accelerated along the microtubule direction, but there is also viscosity, which causes resistance, as well as the structure of microtubules is resistive to perpendicular flows in particular. But what's very interesting is that they are also forming cylindrical capacitors. Well, I'll show you the measurements and the results. And finally, there is also the possibility of forming helical conduction pathways, giving rise to induction. So you can represent a microtubule as an RLC circuit with actually saturable capacitance, because there's only so many charges you can compensate by attracting them to the surface. I mentioned cell division, mitosis, but microtubules also densely fill axons and dendrites of neurons. So all this electrical activity is suspected to play a major role in our brain, and that's the title of this session, and that's the connection. I will not be speaking about it directly. Akihiro will talk about it, but I'm building up the experimental summary of the results that were recently obtained. So the first set of experiments that we conducted was to measure conductivity of microtubules using semiconducting characterization device Keithley, as you can see here, with these microfluidic devices built specifically for it, and with the electrodes between which microtubules were placed, and you can see microtubules on the left imaged and showing disorganized clusters. So these are the results of the measurements at low ionic strength, 4 millimolar potassium. We obtained microtubule conductivity that was, as a function of frequency, peaked at around 110 kilohertz, which is very close to the frequency used therapeutically by this company Novocure from Israel in the so-called TT fields for treatment of brain cancer. So that was very encouraging. However, as we later discovered, this ionic strength, for which a clear signal was observed, is not really physiologically relevant. So there was one data point, so to speak, and we needed to go deeper. And so we proceeded to measure both conductive and capacitive properties of microtubule networks in solution. And in these cases, we used ionic strength, which were closer to physiological. And these are images of different concentrations of tubulin from 0.2 micromolar to 2.2 micromolar to 22 micromolar of tubulin with 100 millimolar potassium concentration. And we measured these systems. and we obtained something quite different from the previous measurements. Namely, in this case, it was clearly demonstrated that pretty much at all frequencies which we measured from 0 to 1 megahertz actually, capacitance of microtubules was greater than that of free tubulin, and that was greater than solution, although free tubulin doesn't have a very strong effect on capacitance of solution, but microtubules do. On the other hand, the opposite happened for resistance, which was somewhat baffling at the time. We found that microtubules actually were more resistive to ionic flows than tubulin, it's free tubulin, and that was even more resistive than solution, the buffer solution itself. These are the tabulated results for tubulin at different concentrations, the one that I mentioned to you. Capacitance C and resistance R, so CMT for microtubules in farads, and resistance in ohms. And we extrapolated these values from networks of microtubules, as you saw, to a single 20 micrometer microtubule, which is a typical size of a microtubule in most cells. And you can see here that resistance of a microtubule like that is about 4 gigaohms, and capacitance about 2 picofarads. And there is also, you can extract from these measurements also the inductance, which is very small, about femtohenry, 7 femtohenries. So to summarize this part, we found that at low ionic concentrations, microtubules increase conductance of the solution. So at low concentrations of ions, they are biowires. They conduct ionic flows. On the other hand, at high ionic concentrations, they do the opposite. They are very resistive. So that's kind of intriguing. You can see a transformation of one system from one type of property to another. The question is, at what point in concentration does it change, or where is the crossover? And we've calculated this, as I'll show you later. But this is a summary of the RLC parameter values for microtubules, experiment and theory, which was earlier published for the transmission line based microtubules. And we obtained these values, which are very close to the experiment. But all of this scales with length and ionic concentration. So that makes it very complicated, but not impossible to solve. One interesting thing that we obtained based on these values, that there could be something like a resonant frequency, microtubules being resonators of electromagnetic interactions at about 650 gigahertz. Based on these numbers, we should find a resonant frequency. And my colleagues in the Department of Physics, Professor Hegman, with his student Cam Howe, actually used terahertz generators to influence microtubules in solution. And you can see here on the right that you can actually break microtubules with this terahertz radiation when exposure is for about 15 to 20 minutes or so. They're broken into pieces. So you have to have a specific intensity, which I have no time to discuss here. We're just submitting a paper on this right now. Now, the next set of experiments should interest this audience, because it talks about the properties of the solution and how that affects the microtubules. And here it's electrophoretic mobility of both tubulin and microtubules moving in the direction of the electric field towards the positive. See some video clips showing you both microtubules at the top and tubulin at the bottom, moving in direction of the positive orientation of the electric field. Now, on the right, you see summaries of experiments which are measuring mobility of microtubules and tubulin, and the zeta potential, which was also measured with zeta sizer equipment at different types of solvents. And I'm going to show you that now, this up close, what sort of solvent we used and what sort of results we obtained. This is for DMSO. And here we see something, sorry, this is pH dependent. Yes, so that's very important. Around pH 5, that's the isoelectric point of microtubules. So you can see here that for pH greater than 5, microtubules are negatively charged. However, for pH less than 5, they become positively charged and actually stable, which is quite amazing. We've imaged that as well, showing that positively charged microtubules can exist. Then we used DMSO concentration, and here you see the mobility decreasing and actually even reversing. So at concentrations of DMSO exceeding 80%, microtubules again become positively charged, which is quite amazing. This has never been seen before. And yeah, and we also use glycerol, and for glycerol there is also a crossover in mobility, although zeta potential is consistently negative. Glycerol is in yellow. So the zeta potential is not much affected by the concentration of glycerol. Of course, viscosity is, and this is for 3 other solvents commonly used, MES and pipes and this citric acid, all of which are shown here for different values of pH, and the mobility of microtubules. When it's negative, that means it's kind of standard microtubule negatively charged. When it's positive, it changes charge on the surface from negative to positive. And we see it also in the case of these solvents. We also, using dynamic light scattering, we observed aggregation of tubulin dimers into oligomers at high concentrations of DMSO. And then to try to understand it, we perform modeling using Poisson-Boltzmann equations, modified Poisson-Boltzmann equations actually, to understand the ionic concentration as a function of ionic concentration of microtubules as a function of the bulk concentration, in fact. So we use cylindrical system, which reflects the microtubule, but also Lumen, which is specific, and the C termini I mentioned to you earlier, because they are so highly charged and so flexible and short. So these are the results. In a summary of all these results, the function of bulk concentration and radial position away from, on the left, the lumen, in the middle, C termini, and on the right, outside of the microtubules. And the mystery is solved here. What happens is that low ionic concentrations, the range over which ions feel the presence of microtubules, the surface of microtubules, is very large, extends to perhaps as far as 10 nanometers from the usual Debye length of about 1 nanometer at high concentrations. So that creates a double layer. That's the capacitive aspect of microtubules, and also affects the conductivity greatly. We published these results recently in Frontiers in biophysics, and I'll be happy to give you more details of those of you who are interested. So this is on the left. It's the summary of the local concentration of potassium around the lumen. So inside the microtubule on the outer surface, you have to look at 12.5 nanometers is the starting point. That's the surface from this central axis of microtubule. And here you can see the local concentration varies over a distance about 2.5 nanometers from the surface quite rapidly. And this is the final sort of, on the right, you have the final elucidation of the mystery of what happens if, when you change the concentration of KCl, potassium chloride. At very low concentrations, conductivity of microtubules, plotted here in Siemens per meter, is up to almost 500 times greater. So microtubules at low concentrations of ions become hundreds of times more conductive than the medium. However, at about 100 millimolar, you see the crossover, and there is no difference between the conductivity of microtubules and the solution, whereas at higher concentration, the solution, plotted in red, becomes more conductive than the microtubules, which is very interesting because the cells, such as neurons, could control how to conduct electric signals through its interior, whether through microtubules or through this solution. It can be just a matter of shifting the ionic concentration. I'll show you something also interesting. We used a compound called P4VB, shown here, which is a reporter of the local pH. It changes the emission spectrum as a function of concentration of protons around in its vicinity. And it so happens that P4VB binds to lysines on microtubule surfaces. As you can see here, microtubules with P4VB labels on them, they shine here very brightly at the given emission and excitation and emission values of photons. And this is the summary of the result, which shows you that from about pH 7, microtubules have a local concentration of protons, or pH, up to a single unit lower than the bulk solution. In other words, again, just like they attract ions, such positively charged ions of potassium, sodium, and calcium, they also attract protons, and they vary the local concentration up to a value of 1. The last set of experiments, very briefly, because I know that time is running out, is called delayed luminescence. This was done in Florida by Dr. Dogario, and it shows you here what happens, and it's really very bizarre, with the illumination of a sample with microtubules over 4 minutes in each cycle, separated by about 10 minutes of no illumination. It was uniformly illuminated with a single wavelength of, in this case, 650 nanometers, corresponding to 1.8 electron volts. Both tubulin and microtubules, but more so microtubules, re-emitted this radiation in a delayed fashion. That is, amazingly, photons were still being re-emitted from microtubules after 10 minutes and up to 15 minutes. Minutes, not femtoseconds or picoseconds. It's quite amazing. We still are grappling with this result, but put together a theory with my student from France, Lia Gessa, involving tryptophan networks, which are exposed to electric fields of the tubulin dimer and electric charges nearby. And we obtained a Hamiltonian that was diagonalized with these interactions. And here are the results of the diagonalization, which correspond closely in terms of the eigenenergies to the values that experiments for excitation wavelengths and corresponding to the energies, if you can read them at the top, 1.95, 2.32, 2.72, and 3.21 eV. We came to within about 3 millielectron volts to these values, so it's the energies are close, but the time scale is not yet explained why it takes so long. It has to be a cascade process that slows the re-emission of photons somehow, just like in phosphorescence, I think, but we don't have a clue yet if it's correct or just an assumption. And finally, with the same set of experiments, it was measured if electromagnetic fields can influence microtubule polymerization. I told you about their dynamics, and they do. You can see here the dynamics of microtubules, that is, growth of microtubules from dimers in solution. First of all, starts later. Secondly, the polymerization occurs at smaller number of sites, and the final stage is less dense. In other words, when you shine light on systems of microtubules growing in solution, you get less of that, at least with this particular energy and temperature. So a lot of interesting new possibilities, I think, of electromagnetic interactions with microtubule systems, and that beg for future applications in photonics, computational work, and so on. Let me just jump to conclusions. I'm done. So what I would like to stress is the richness of behavior of individual microtubules vis-a-vis electromagnetic interactions. Polymerization, depolarization of tubulin into microtubules can be seen as a formation of bioelectric circuits, but it all depends on the conditions of the solution in which this is done. Ionic concentration is affected tremendously, and this is even more complex when you build ensembles of microtubules into networks, which we're just scratching the surface. And microtubules can be used as charge storage devices or signaling devices with the memristor property, which I didn't even talk about, but we published a scientific report on it. Thank you very much. I will stop and apologize for this rapid machine gun delivery of the talk. Thank you.
Thank you, Jack. We are open for time of question. So please leave your questions and comment in the chat box. Now there are no questions.
I have a question. Yeah.
Yes, please.
Jack, thank you very much. Pleased to it's fascinating work, and I really was looking forward to listen to that, because I do believe that it is all about water on microtubules, as yes. You might expect. Yes. If you can you please show slide 24. I noticed something that for the moment proves what I think.
Okay.
I think.
Okay. Let's see.
24.
Do you see it? I'm not sharing it.
Yeah, if you can share.
1 second. Maybe now.
Yeah. What I notice here, you have water and zeta potential and also mobility of the water have a very similar pattern. So it's of course variations are a little bit different, but still very, very similar. So do you have some idea about this?
Well, I do, but there's more. We have more results. Actually, I didn't have time to explain all of this. Yeah. I think there are actually, in addition to ions, which we really focused on, I think there's also the formation of ordered structures of water on microtubules, no doubt in my mind. And we've recently performed experiments which actually show it when we measure conductivity of microtubules which are illuminated by light, that changes the conductivity, which means this goes in the direction of Jerry Pollack's theory, right? That you energize the water structure by electromagnetic means, and I don't have the slide here to show you, but we see that happening. So conductivity of microtubules in solution also depends on the illumination by laser light. Amazingly, yes. So water plays a key role.
We did an experiment with 660 nanometers, and we could see very interesting changes in the water structure illuminated by this particular wavelength. So I expect to be able to explain exactly what is happening. I mean, what kind of water structures are forming.
And the first talk of today, I think, could help us too. Would be nice to do molecular dynamics simulations of water molecules around microtubules, and see if there's any sort of spatial correlations and spatial temporal correlations taking place. I think that there is.
Yeah, thank you very much. I think Michelle Sensei will
Okay.
talk a little bit
So
about
we have another question from okay. We have two questions in the chat box. Jack, please see it and respond to them in the chat box.
Okay.
Okay. Okay.
Yes,
So
Thank you.
let's move to the next talk. The speaker, Dr. Akihiro Nishiyama, is collaborating